In the last video, we talked about how we could reason about one kind of interesting subproblem for the knapsack problem. And that interesting subproblem was the problem where you start with an optimal subset, and then of the items in that optimal subset, you remove access to one, and you remove its associated capacity. And we said whatever's left has to be optimal for that reduced capacity, right? It has to be. If it weren't, then the first subset we were looking at wouldn't have been optimal in the first place. Okay, so now that's one kind of clearly optimal or clearly interesting kind of subproblem. It's clearly, like, that subproblem is clearly relevant to the solution to the overall problem. But there's another kind of subproblem that is also relevant that is not quite as obvious, and it's almost trivial, right? It almost doesn't feel like it's something we need to look at. So let's think about this other kind of subproblem. So now suppose I start with this. So I start with my truncated problem where my capacity, let me draw a line here so that posterity can tell what's going on. So my capacity is 5. I'll do capacity prime. My n prime is 1, 2, and 3. And so, you know, it's a fully specified knapsack problem. It has an optimal solution. We reasoned about the optimal solution last time. So my optimal solution is just item 3, right? If you don't remember why, look in the last video. So just item 3 with a weight of 4 and then 1 unit of empty space. So now what if I came to you and I said, all right, I see you've just solved this problem. You know, suppose you've solved this problem and you have an optimal subset that contains just item 3. And I said, now wait, let's generate a subproblem, like let's generate a smaller instance of the knapsack problem, and now figure out the optimal subset for that. So now what if I say, here's a new problem, a new instance of the knapsack problem, and it goes like this. Same capacity, W prime prime is 5, but now my n prime prime, right, the set of objects that are available to you is smaller. And now it's only objects 2 and 3, right? And I say now, what is the optimal subset among items 2 and 3 when the capacity is 5? What is optimal subset? And you'll say, it's just 3, right? Obviously, it's just 3 because it was 3 for this one, and you haven't done anything relevant to the problem. Like you told me, like I wasn't using item 1, and then you came and said, you know, now you can't use item 1. Does your answer change? No, the answer doesn't change because 1 wasn't relevant to the answer. 1 was not contained in the optimal subset for the problem up in parentheses up at the top. But it can't be contained in a subproblem where I'm not allowed to use 1. Like it is irrelevant that now in this prime problem I'm not allowed to use 1. So the optimal subset is obviously just 3, the same as it was above. And so there's no change. Like if I remove access to an item that isn't in use, that doesn't change the optimal subset that I'm looking at. So now let's think about how we could kind of phrase this in language of subproblems. And then in the next video, we'll start to put this together into an algorithm, right? We'll take this and we'll actually start to write it down mathematically so that we can build an algorithm out of it. So the interesting subproblem, let me write it like this. So the interesting subproblem for the knapsack is one that looks like this. One, there could be possibly a smaller capacity, right? To generate an interesting subproblem, we may or may not reduce the capacity of the knapsack, depending on whether or not an object is being used in the optimal solution. So I'll say possibly smaller capacity. And then second, one fewer item available. right? And this appears to be it, right? This appears to be the specification, the very, very informal specification of what makes a subproblem interesting for the knapsack. Now, why is that, right? So what we did here is we kind of went backwards from an algorithmic perspective. We said, let's imagine that we have the answer, and now let's start pulling things out of the answer, or paring down the problem definition to reason about stuff. And that doesn't help us from an algorithmic perspective directly, right? To imagine that you begin at the end isn't an obvious way to write an algorithm. But what we can do with this is we can say, suppose now that I have the optimal subsets for all of the subproblems of the knapsack problem, right? All of the problems where there's less capacity and fewer items available. Right, so now let's imagine that we have all of those answers. Then to build a DP algorithm, what we do is we say, which of those are the important ones to solve the overall problem? And what this suggests is that there are two, right? There's one where we remove access to item 4, and there is a reduced capacity. And then there's one where we remove access to item 4, and there is not a reduced capacity. So we're going to build this out, and we're going to work through example problems and fill out the DP table and write down the math to make sure this is clear. But this is the idea. The idea of creating this DP algorithm for the knapsack problem is going to be that we're going to go solve a bunch of subproblems where we have fewer items available and a smaller capacity. And then we're going to come up with a systematic way of combining the solutions to those subproblems into a solution to the overall problem.